some of it upon you. So Dave Moffat's going to work you through an exercise from our MW curriculum involving pulsars.
So I really enjoyed the surprise Dan threw at me a couple of days ago. Hey, Moffat, you're going to do a thing on pulsars. Okay. So here we go. Anyway, I have a small background in pulsar astronomy myself, and that having access to a radio telescope on the Skynet on the Skynet system is actually a really cool thing, and it's actually something that it's easy for you guys to actually follow along. So before I go too much further into that, let me just again do a small background because pulsars were discovered serendipitously in the late 1960s by Jocelyn Bell. She just happened to find scruff on basically a chart recorder that led to the discovery of probably one of the most significant finds in astronomy. And they're one of the most compact objects you can find other than a black hole. They actually are the end of life for a star, a massive star. But at the time of their discovery, it really wasn't really sure what they were. But her discovery, again, serendipitous discovery that it was one where, again, led to a better understanding of stellar evolution. Now, of course, it's led to other things like album covers. In fact, this is Pulsar 1919. This was the first pulsar ever discovered. And of course, you can actually get this on a T-shirt if you want to. Now, the discovery at Cambridge actually opened a door to, again, a set of sources for which are still actually being observed very actively today. Her discovery was, they found a periodic source of radiation, of radio radiation. They had a period of about 1 1/3 seconds. And the first thought was, well, if we tell people now, they're going to think they're little green men. Well, it's a good thing they found more of them and that they had different periods because that wasn't true. But now, after some thought, they thought, well, what could actually generate radiation like this, pulsed radiation? And the first thing that came out in the first papers was maybe it's a oscillating white dwarf. And that wasn't really going to generate the radiation that was observed. And then they had to go back to a paper, an obscure paper from the 1930s by Bod and Zwicky saying the end of life of a massive star could actually be a neutron star. But what really tied it was the fact that we have historical observations of supernovae, and it turned out that this one, the supernova of 1054, actually has a pulsar in the center of it. So that actually tied those two things together, the theory of a neutron star plus the discovery of a pulsar in a supernova remnant itself. So the pulsating radio sources, pulsars for short, they have rotation periods from about 1.4 milliseconds. And one of the later discoveries is one that was discovered that had a period of 76 seconds. Their masses inferred from binary orbits, about 1.4 to 3 solar masses. The size is have a radius of about 10 kilometers. So it's as big as a city, more massive than the sun, and can rotate up to 700 times a second. So we're looking at something that's really extreme here. But the thing that actually we can use to our advantage is that this is pulse emission, and it's at radio, and it's because there's a constant beam of radiation pouring out from the magnetic pole of the star, and we can actually, if it sweeps by our line of sight, it's like a cosmic lighthouse for us. And that's the advantage that we're going to use when we go to actually observing one. The geometry that we've inferred from our observations makes basically it's like a giant dipole magnet rotating in space. The magnetic fields are a million times, basically a million times a million Gauss, and they generate electric fields of basically the same order of magnitude in volts. That actually accelerates charges, and the accelerated charges actually generate gamma rays. Those transform to electron-positron pairs. And that continued charge acceleration actually creates what we call a pair cascade that generates basically a pair cascade that generates more electrons and positrons, and those continue to be accelerated until you generate a beam of radiation, which we also call curvature radiation. Now, key to this part is that radiation is highly polarized. And we're actually going to demonstrate that this morning as well. All right, so let's see. How do you do this? Well, in order to see a pulsar, the best way to do it is to use a radio telescope. And of course, all the best radio telescopes in the world are oversubscribed, and we basically can't get our hands on these more famous telescopes like Parkes or the GBT or even this one at Jodrell Bank. But thanks to Dan and his group, we have access to that little one that's circled in red above the GBT, the 20-meter radio telescope. And we are actually going to try to go ahead and start a radio observation right now. So what I'd like you to do, if you have a chance, is I'm going to leave this up just long enough. Go to tinyurl.com/skynet-workshops. Go ahead and do that right now on your computers. I'm going to give you just a second. And I should have had Reed put a 30-minute timer on my talk,
I was going to ask him. That'll look
but
fun.
now it's been more than 30 minutes.
I'll keep track.
Thank you. Because once you've logged into Skynet, instead of using that optical observing feature of Skynet, you're actually going to be using the radio observing feature. So I'm going to go ahead and open up on Dan's computer here. I'm going to go ahead and open up Skynet. I think no, that's not it. Read second. This one? Yeah, this one. So if I, no, not really.
One to the left.
One to the,
I overwrote.
you overwrote it. Okay,
It's easy enough to do.
thank you. So you're actually going to go to My Observatory, and you're actually going to go to Radio Observing here. And when I go to Radio Observing, the very first thing you're going to do is add a new observation. Now, it turns out setting up this observation is actually much easier than setting up an optical one. But we're going to go ahead and do that. Add new observation. You'll see the same kind of page that you normally would when you start an optical observation, but the features are just a little different. Now, there's a built-in pulsar catalog in this system. So the first thing you're going to want to do is actually preface every observation of every target, or every target is prefaced with the letters PSR. That way it looks into the catalog, the pulsar catalog that's built into the system. And the target I'm going to have you observe is actually one of the brightest pulsars in the northern sky. Now, when we add the new radio telescopes in the southern sky, we got a whole bunch more down there that we can use. But for today only, let's do this. This is one of the brightest pulsars in the northern sky. It's B0329 plus 54. And pulsar names are basically right ascension, hours and minutes of right ascension plus degrees of declination. And these are 1950 coordinates because they were discovered in that era, and they do have 2000 names, but for now, let's just do that. And if you hit search, it will automatically go to, it'll actually show below that it found it in the catalog, and then it goes ahead and it preloads the coordinate type. I think I can zoom. Okay, that was crazy. Right there. That's what I'm putting in the system. And Jonathan has like prefacing a fight in a anyway, he's got the name of the pulsar on his little card there. Red doesn't show up. Okay, so once you have this in, you just save and continue. Well, first of all, please, if you look at the visibility chart below, you'll notice that this pulsar is up right now, which is really cool. Now, you're going to go ahead and you're going to save and continue. And the next screen is actually, this is usually where you would choose a filter and then subsequently choose a telescope. You're just going to leave this just like it is because by default, it sets it in low resolution mode, which means it's the spectrometer that's built into the system is already set up for the frequencies that it's supposed to be centered at. We're going to use the H1 filter, which is an 80 megahertz band filter that's attached to the spectrometer. So you can't do anything with the number of channels. There is this thing called pulsar mode. Do not click. I know it's deceptive. We want to look at a pulsar, but this will turn on a piece of software that we have no control over called Presto. It's run by the Green Bank Observatory. It actually will pre-fold and pre-process all the data for you. Oh, you could do it if you wanted to. It's actually pretty neat to see the output. But what we want to do is we want to look at it ourselves. Uh-oh.
Hi.
Uh-oh.
Eat the mic.
Eat the mic? Okay, I'll eat the mic. Save and continue. And then from all the plethora of accounts that you've been given over time, like Dan's here, oh, he's got lots of credit. I wish I had this much credit. You just pick an account. Most of you probably only have one, and make sure you're in track because we want to track this source. Duration. Now, normally, if you're doing optical, you go 60 seconds to 120 seconds. Do the same, 60 seconds. However, the integration time here is quite important because some pulsars have periods that are less than 0.3 of a second. And if you put down 0.3 of a second, you're going to completely miss it. So you're going to want to use the smallest number you can that the recorder can actually record. And in this case, this is basically 0.021, which is 21 milliseconds. So be sure to put down 0.021, and that's in milliseconds. It can go shorter, but you take a risk because if the system goes too fast, it might actually skip samples and it may actually not even record at all. We've experimented and we've gotten lower, but this is the safe part. And at this point, you can hit save and continue, and no repeats. You don't have to repeat. Like, we're not integrating multiple scans. And then once you've gotten past the account screen, you can go ahead and submit. And here's the thing. I'm having you do this in real time so that you can go back in later and look at your data. However, we're going to be looking at a data set we recorded just earlier in the week or last week, right? And we're going to have you look at that because you're going to do the same processing step when you get to that point. Okay, how am I doing on time? No clue. Okay, that's really cool. Now, if you go back to the Skynet workshops, because this is submitted and it should be in there and it should show up here as your observation and that it's ready. So, so at that point, we're done with the observing, putting an observation into the queue, and now it's time to actually go to going back to processing. So, we've given you in that little workshop that Skynet workshops Google Doc, we've given you a list of pulsars that you can attempt. We actually did the first one, Pulsar BO, 0329 plus 54, because it's really easy. There are more, and their difficulty levels go up. The difficulty meaning they're fainter. All right, so you've already turned in these observations. There's a little descriptor here. There's some descriptive images that show what we've just done. And of course, we do have links to what it should really look like. But what I'm going to do is I'm going to skip ahead a little bit. And I'm going to go to this, what we call curated pulsar list. This is one in which Stan Converse actually went through and observed all these pulsars on his own personal initiative and actually recorded this in advance. So I believe they were just default settings. As long as it's not within 10 degrees of the sun. I think that's the default. And there's a little secret I'm going to let you know. You can actually set the elevation limit down to 0. You can actually make the antenna point all the way to the ground if you wanted to. I would not recommend that, of course. But anyway, so what I'm going to do is have you, if you go through here, you click on the number. These are observation numbers that are actually part of Skynet's archive. So this is in the Skynet Workshops Google Doc, which I provided a link earlier. And if I click on this, it will direct you to one of NREO's records that shows you what the observation will look like when you get it back. If you don't see the screen, you're not there. Are you there, Kevin? Okay, good. Calay's there. Excellent. Can you see the pulsar already? When you look at the panel on the bottom left, that's amplitude versus time for both polarization channels. The receiver itself actually has X, Y, or has horizontal and vertical dipole feeds that record the orthogonal polarization of the electromagnetic radiation that's entering the receiver. So this is a receiver that's sensitive to polarized light. You're actually looking at you're basically looking at orthogonal radio polarization information coming into there, and you can actually see the individual pulse spikes in that record. And when I say it's the brightest pulsar in the Northern Hemisphere, I'm not lying. Now, when we look at the other sources, the fainter ones, they'll be buried in the noise. How do we find it if it's buried in the noise? These you can see by eye, but how do you find ones buried in the noise? That's the trick. Over on the panel on the right, that's the spectrum of the spectrometer. And the only thing of note is that what it's doing is it's equalizing all the amplitudes that are coming across the spectrometer. But there's one it can't get rid of, and that's that spike here. And if you scroll down to the bottom, you'll notice it occurs at about 1420 megahertz. That's 21 centimeter wavelength. As you might know why that spike is there. Well, if you're a radio astronomer, it's probably one of the most common spectral lines that occur in. Yes, the hydrogen spin flip transition, that's right. So if you see that one there, you're okay. If you see another spike in there, you're not okay. You should probably throw it away. The other spike occurs around 1380, and it's a local radar, airport radar, I think, nearby. Anyway, now there's two ways to look at this, or there's a couple of ways to look at this. You can go to Live Continuum, and if you click that button on the bottom left, you can actually zoom in a little bit on this figure. But what I want to do is actually have you start processing it right now. So in the time that we have. So the first thing you're going to do, if you go to the top sort of left, there'll be a panel that says Continuum. You get choices like raw data, calibrated, and calibration info. You're going to want to select calibrated. And if you click calibrated, and I'm waiting for this to come back, it's going to give you an ASCII text file that has all the information associated with amplitude versus time.
Coming?
It's coming. Is it coming? Sweet. This is the one I was looking for. Weaker one. Okay. That may be it. Yep, that's the one. So this is the calibrated amplitude versus time. Now there's a big header at the top, and you can see things like, for example, you can see there's an observation ID. That's the one that we grabbed from the Green Bank site. There's also the integration time, which when Stan did this, he did it at 4 milliseconds. Or what is so it's faster than the one I just suggested that you do. And then down below are the timestamps for every record, right ascension, declination, azimuth, elevation, and then this is the amplitude in both polarizations. And there's some other additional flags here, but more importantly, you're going to want to save this file to your computer where you can find it. So I'm going to say save as, and considering I don't know where this will go, I'm just going to put it in downloads on Dan's computer here and save. And we'll grab that in a little bit. Now, is everybody at this point, before we do the next step, you got to make sure you save your file. All right. All right. Now, when you're ready, you're going to want to do, if I go back to the Skynet Workshops page, you're going to want to use what's called the graphing tool. And that's basically, you just say tinyurl.com/Skynet-graph. And if I do that, then that will take me to this. Are you an Opus student? Well, ignore that question. There's the new graphing tool, which will be demonstrated, if not already, it'll be demonstrated later today. But then we need the old tool because it turns out the Pulsar tool hasn't been updated yet, but there's no need for the update because this is what it looks like. Now, the first thing you should do once you see this page is on the top left, there'll be a drop-down menu, and you're going to select Pulsar. It preloads a fake data set in there. That's not our data. That's just a fake data set because what you're going to want to do is upload the file that you just saved. So at the bottom left is a tab for uploading the data file, and then you just choose it from wherever you saved it. So in this case, I'm praying I can find it. There it is. And then we'll go ahead and say open. And it might take it a few seconds, but that is the data file that I recovered from the Green Bank data that Stan recorded. So you can actually see the individual pulses already in the system. What happened? Okay. Now, here's what's really cool about this. From this point, you can actually do one really cool thing. On the bottom right is a tab that says Sonify. Go ahead and try it out. What you're hearing is the data record. And you can time it. You can actually use a stopwatch and time it yourself. But we want to do a little better than that, right? We want to find out what is the true rotation period of this pulsar. So, I need the old one. So I'm going to go ahead and stop the sonification. And the magic tool behind this is we want to find out, because this is a time series, you want to find out what the period is. Now, back in the old days, I'd say, do the Fourier transform. Problem is, this data was asynchronously recorded. That is, from one period to the next, the number of samples is irregular. So we're using what's known as a Lomscargel periodogram that actually will allow you to bring in irregularly sampled, data. So if you choose at the top left, you choose the periodogram button, then it preloads a set of start and stop periods. You can go ahead and use that and just hit compute. It might take it a little while, but it will bring back to you a periodogram, basically amplitude or power, the power spectrum of the time series versus period. Now, this will vary from pulsar to pulsar. And sometimes if the noise level's too high, you may get a lot of garbage here. Having a knowledge of what the period of the pulse is actually key, and that's why I provided a curated list that has the period already loaded in it. But from this particular one, the strongest feature on this power spectrum happens to be at about 0.7 seconds, which is roughly what the period of the pulsar is. If you mouse over that point at the very top, you will see the first number in that column, that first number that's displayed is actually the period of that point. So I'm getting 0.7149 roughly seconds for that one. What's really interesting is you can probably find, that's the fundamental period. You can actually find one of the harmonics below at about half of that. If I go down to the next feature, it's about 0.3583. That's roughly half the period or twice the rotation frequency. So you're actually seeing, and here's where my knowledge is a little flaky, fundamental and first harmonic, or is it second harmonic and first overtone? That I always confuse the two. Anyway, that's the period we're actually after. 0.7149. Now, we're using this information to actually go through and stack each period so that we basically stack noise on noise so that the noise goes down and that the true signal, if there's signal buried in the noise, it will come up. You have to have the precise period to do this. So what I'm going to do is go to the next tab that says period folding, which looks like a bunch of garbage right now. But if I go to, I can set the period with either a slider bar or I can basically go through and backspace and actually enter the period manually. Of course, this would help if I, Dan, got to type fast apparently. Okay, just mouse over. Okay, there we go. So we rounded it up to 0.7145, and bang, there you are. There's your pulse. But what you've done is you've basically taken 60 seconds worth of pulsar data, and then basically for every period, you've basically stacked each period on top of each other and averaged it. Now, the display shows 2 periods. You can actually turn that feature off. You can say just show 1 period. But actually, but I kind of like it with 2 periods. You can actually see, because for one of them, it shows it at the edge. I'd rather see it near the middle. Now, you're almost done. Because now if you sonify it, less noisier, less noisier, much stronger. The signal noise, you've just improved the signal noise greatly, and you can hear every pulse now, or you can hear the average pulse. All right, so we're almost done with this pulsar because the, I didn't mean to do that. Because one of the really cool things is because we used a polarized, an orthogonal set of polarized receivers. I said earlier that pulsar radiation, the curvature radiation, is highly polarized and is actually aligned with the magnetic field of the pulsar. So if the pulsar's beam sweeps by your line of sight, the magnetic field actually will sweep across the line of sight as you pass, as it rotates past your line, or sweep by you as it rotates past your line of sight. Which means the direction of the magnetic field is changing, which means the direction of the polarized position angle itself sweeps. Now, unfortunately, we don't record all the Stokes parameters for this, but we have two of them, total intensity and also the difference between them, which is actually what we call Stokes Q. So if I click Show Difference, it shows the difference between the two. Basically, this is the same as X minus Y in polarized speak. Now, there is an amplitude differential between the two, an amplitude differential between the X and Y polarizations. Their amplitudes aren't exactly calibrated. There is a follow-up procedure in the workshop, or Skynet workshop Google document that shows you how you can fix this. It does involve observing a calibration source. But if I show the difference between the two, I'm not a PC person. You can adjust the calibrated difference between the two. If I even move it to say roughly about 1.3, normally if they had equal amplitude polarizations, that is if the source was unpolarized, that should be a flat line going across. It's not flat, is it? In fact, you can't make it flat. Just changing the amplitude back and forth between the two, you can't make this flat. There's nothing you can do with that. Which means what you're looking at is a linearly polarized source of radiation. The pulsar has a high degree of linear polarization. And if we had ability to observe Stokes V, which is circular polarization, it's actually got a lot of circular polarization too. And there aren't many circularly polarized sources of radiation. Pulsars are one, solar, radiation above sunspots is the other. And Jupiter is another one. But again, it's even weaker than this. So anyway, and Jonathan is saying, please listen to this in stereo because you can actually hear the sweep from X to Y in stereo because it actually broadcasts it. Yeah, in fact, here, if I do it again, if I play this in here. You can hear it in one speaker system before the other. Like a double beat. You hear it? Yeah, I know there's three components. Okay. I'm going to stop there. I'm going to ask for time, see how much time I have left. 0 time? Dan, are you keeping my time? Am I done? Am I out of time? I could.
Sorry, stop it. Are you done? You're asking if you can stop?
No. We're out of time. We can always throw more at them.
Let me see. Couple minutes.
Oh, 2 minutes. Okay. I'm going to throw a fast one at them. All right. So,
Dave.
it has to do with this pulsar actually has structure. You can almost see it. Yes.
I got a text from Donovan 5 minutes ago. They're out trying to get some. And 5 minutes ago, they asked if we
But the food's out there. The yogurt's out there.
not
Not all of it? Okay.
So we have a few minutes. Let's do one.
So what I'm saying is, if you take a few extra minutes, I
Okay.
Yeah, we can do that.
getting us our snacks would appreciate that.
Well, no, we'll do one of the ones that has a recording already. Yeah, so we're gonna go from one of the slower ones. This is about 1 second, 1 second period. I'm gonna go back to the Skynet Workshops document. And Dan had actually created this document. He actually preloaded it with links to 3 pulsars that are actually a bit faster. In fact, I'm going to ask you to, and I believe it's the first one, or is it the last one? I think it's. Yeah, everybody can pick one. I'm going to pick the last one myself. These 3. If I choose the last one now, these are records that have already been folded. They've already been folded for you. And it'll be a smaller header. And as you scroll down, there's only about 127 records or something like that. But you're going to want to save this to your directory. I assume it went to the same place. Okay, so now Skynet, the graphing tool actually knows how to load this data. It's been pre-folded, so you don't have to do the periodigram first. You just basically go to upload data file and just choose that file and go ahead and open it. And it goes ahead and loads it into the folded spot. And because it's been pre-folded, the plotting program actually shows the period up there in seconds. I want you to notice the period. The period for the last pulsar was 0.7145 seconds. This one is 0.00139, or about roughly 1.4 milliseconds now. So when you get that loaded, hit sonify. I'm not going to sonify it. I want to hear you sonify it. What this is a record of is the fastest known pulsar, which has, again, a period of 1.4 milliseconds, which means it's rotating with the frequency of just over 700 hertz, or 700 times per second. When you think about it, if you're standing on the surface of this pulsar, you yourself are almost rotating with the surface at nearly the speed of light. That's how crazy this pulsar is. They don't know if they're any faster, because any faster would imply that they would disrupt, as the star would basically tear itself apart as it's rotating. I'm going to go ahead and sonify it on this side.
Okay, so you got to load it.
That's
Did you
close
upload
to
data yet?
which musical note?
Okay, let's load it in. Let's take a look.
Like, what is 660 hertz?
Okay, so that is
That's a
actually
musical
data.
note, right?
You may not hear it in the individual ones. You could try sonifying.
660 is
Maybe there,
yeah.
maybe not. Okay, stop. Let's go to the
E.
periodogram.
Yeah, so it's just above
And,
E
uh,
or something
hit
like
it.
that. All right, now there is one more pulsar because, Stan insists. It's actually in our curated list, and it's actually this pulsar right here. It's at the bottom of the list. It's basically B0833 - 45. If you feel brave, you go ahead and choose this one and
Oh, no,
save
what
its
he's doing,
data.
Slide up.
This one is the brightest pulsar in the southern hemisphere. And it's located in the Vela supernova remnant. So this is known as the Vela pulsar.
Hold them. There's
It rotates
dispersion
11
measure,
times a second.
basically, as the radio waves are coming through interstellar space.
So if you want a challenge, go ahead and try that one. and go ahead and fold it and sonify it so you can hear it. It sounds more like a trolling motor for a fishing boat or something. It's kind of that period. The period's about 89 milliseconds, and it has a rotation frequency of about 11 hertz.
That's the fastest one at the bottom.
This one?
Yeah, so download that. Click on it. Then upload that one. Wherever the tool was. Data. It's all pre-processed. Load your page, maybe something got Pulsar. Curve to Pulsar. Try uploading it again. Upload data. Load that in. Yeah, it's been pre-folded. Oh, you're already past the periodogram. It's pre-folded. You go
Oh.
straight to sonifying it.
So,
No, this is
No.
the folded light curve.
oh, this is.
Yeah,
oh,
you can't do
okay.
a standard periodogram because the dispersion.
Yeah, so how do you,
It
is it?
there's software that so you imagine a plot
Pardon?
of time versus
So
frequency.
you get it from the data. You're
Yeah,
not,
you get
don't-
from the data.
And it, you just, the assumption is it's some smooth function of frequency and you
Mhm.
fit to that.
And you can see it, and then you kind of shift everything to be at a common, and then, yeah, it's a more complicated analysis than what we learned to do with interest.
And there you go. If you have any questions or questions about how you process these, or you want to try your hand at one of the more challenging ones,
Yep,
But-
yeah.
interpreting their periodograms can actually be a bit of a challenge. But again, you do have a hint. You do have a hint because on the curated list, we actually list the periods
Of the-
from literature.
Yeah, you can study
And,
until a medium
but the
level. We don't
the
try
periods
that
from
in this
literature will not match what you get because these observations were taken a while back. And as we know, the
Good
Earth
job.
turns, the Earth moves around the sun. And of course, the sun goes around the Milky Way, and therefore there is a Doppler shift to the period that we record.
How do you?
So it changes that about the fourth place in the period, it actually can change that number.
Yeah, and no,
That's
how
how
do you-
great the effect can be. Any questions, guys?
A little out of my area. I'm not a radio astronomer. Yeah. So, any questions for Dave? We got a question over here.
Thanks for doing the demo. I'm wondering with with exercises like this, just bringing back to our previous session's conversation, how much detail on what's going on in this, like what we're plotting, like the idea of polarization or the idea of period folding, do tend to go into? I know there's not one answer for this, but just in an intro level astronomy class, I could see this being pretty plug and chug without understanding if we aren't able to get to the details of these, like what what is being folded, what does that mean?
So this is from our MW course, and Jonathan may have an answer, and Dave may have an answer. This is from our MW course, and I'm sorry, Calais. And Calais has an answer. On the computational side, what we can do is place a limit on the size of the neutron star, because just the circumference divided by the period has to be less than the speed of light, or maybe I got that around. But and you start with the slow ones they can do. We have to the ones they're observing. And you probably said this. They're purposefully slow because the faster ones you have to do a dispersion measure correction, much more complicated. And then after they've done this, and they love it almost as much as the imaging, maybe as much as the imaging projects. The sonification part's really cool for them. And then once they've done the ones they can do, we can get down to maybe a few tenths of a second with this technique. Then we give them those 3 that are already dispersion measure corrected, and they go faster and faster and faster, and you can get the limit on the neutron star down to like 60, the radius or diameter is less than 60 kilometers, because you're getting close to it rotating at the speed of light. And so that's the little quantitative bit that we get out of it. But the key thing is it's a nice introduction. There are all sorts of things you can do in the radio. This is perhaps the simplest thing. You just point at it. We could do spectroscopy, we could do mapping. We'll do some of that on the last day, but this is a nice introductory exercise for them to gain familiarity with radio.
So to address the engagement for intro astronomy, engagement is off the charts for this activity. I've done it many times, and this is why students are taking astronomy. They want to learn about like crazy dense things spinning at near the speed of light. I do a lighter introduction than depending on the class for some of the classes where that's not as calculation heavy. So something they don't learn how to do from this is period folding. They don't really know what that means even after they've done the activity. I have them build except when they watch Kate's video because she made this amazing video about it. But I have them make models based on their understanding of the pulsar. I did that for the first time last year, and it's going to be a fixture from now on. They were so creative. They had so many cool ideas. I was like, you have to model the rotation of the pulsar, an offset of magnetic and rotational axes, and the one other thing, the pulsar wind, which is in part of the buildup that they have for that. They got super into it. I have some amazing videos that they made and just blew me away with their creativity, and I bet they're going to remember it because they made it.
And kind of the more advanced aspect you saw was the polarization aspect. Maybe you don't do that with the intro students, but in our MW course, it's all about different, it's optical and radio, so it's about all the different light emission mechanisms, Bremsstrahlung, synchrotron, H1, which you saw a little bit of, and thermal. And so this is a great introduction to synchrotron. The polarization says it can't be thermal. Thermal's not polarized.
There is a resource associated with this. And again, if you have
We
this
ready with the
link
cream cheese?
to this workshop's link, there's a guide which is actually a very descriptive guide that Dan wrote for his class this semester, or was it a year ago? About roughly a year ago. And that's actually pretty comprehensive. There's another link below that. Where is it? Oh, it must have been further up. It's to a press book. It's an open press book, and it actually takes up a chapter in that, and it's even more descriptive than Dan's module. So there are 2 versions of the same thing. And the version that's in the press book actually goes over radio astronomy. It has a pretty descriptive intro to radio astronomy in it. So I would actually recommend both of those resources to read. And at least with Dan's module, you actually have links to videos. I'm just going to go ahead and click on this DR's module 5B guide here. And he actually describes describes pulsars, it has actually a better figure for what the pulsar's magnetic field looks like, and then also an explanation about curvature radiation and polarized light itself in this document. So I encourage you to follow that link, and that I think will help you decide which part of this do I want to use from my class. Because again, your audience might not understand this, but then you get to pick and choose how you want to explain it. Yes. That's what this module 5B is, to some degree.
Well, this is from MW, so they end up here because the cream cheese has May. Over to May. Where are we going to do the group photo?